Hello students, welcome back. Now we are going to talk about the counter designs. So the first one we are going to design is an up counter. So we will talk about that how the up counter will work. We'll design an asynchronous counter using JK flip-flops and we will implement it with behavioral coding style. So let us get started. So up counters, as the name suggests, they are going to count in the upward direction. The count value will increase in every clock cycle. If I have n bit, then I can count from 0 to 2 raised to power n minus 1. And once the counting is at the maximum value, it will come back to 0. A 4-bit counter, if we take as an example, it is going to count from 0 to 15 and it will repeat this pattern. Now let us talk about the asynchronous counter design. Here we have 1-bit version where we have JK flip-flop. Both the inputs of J and K are connected to 1. That means in 1 input case the output will be toggled. So therefore after every positive edge of the clock, Q will toggle. 0 will become 1. In the next clock cycle, 1 will become 0. So effectively, after every 2 clock cycles, 1 more clock will be generated at the output. And then we can wire more such JK flip-flops to generate more number of counts. Let us do it for 4-bit now. So here we have the circuit diagram. As you can see that when we have the first counter here and both J and K are 1 1, that means we are generating 0 1 0 1 0 1 and so on at every positive edge or the negative edge of this clock. After every 2 clocks, 1 clock signal is being generated, 1 rising edge is being received after every 2 clock cycles, and then we are again getting 0 1 0 1 pattern here. So after another 2 clocks we will get 1 here and then here. So using n number of bits we can create from 0 to 2 raised to power n minus 1 numbers, and then all these numbers will roll back to 0 and the counting process will continue. Now let us talk about the design aspect. We need only 1 clock to synchronize the whole counter because we need to provide the clock only at the first flip-flop or at first bit of our counter variable. It can be designed using behavioral coding style also. You have seen the block diagram using JK flip-flop. Use the technique of module instantiation and very easily you can design a 4-bit asynchronous counter. But what we are going to do, we will also explore that how can we design it using behavioral coding style. We need only 1 input, that is clock, and we will have output variable which is count. Count will be a 4-bit value. So now let us go to Vivado and see that how do we implement it using behavioral style in Verilog. I have written the code which is counter 4-bit asynchronous. There is 1 input which is clock, there is 1 output which is count. I have taken clock as a wire and count is a register which is 4-bit 320. If you want to implement 8-bit or any number of bits, you just need to change it here. Now we say initially set the value of count to a 4-bit number 0. Then always at the rate positive edge of the clock, count of 0, that means the LSB, least significant bit, will be flipped. It is note of that, right? Now what we need to do, the next higher bit, which is count of 1, should not be controlled by this clock, okay, but it should be controlled by the output of LSB. That means we are saying always at the rate positive edge of count 0, then flip count 1. At the positive edge of count 1, flip count 2. At the positive edge of count 2, flip count 3, and keep doing it for as many bits as you have. Now let us check the simulations. The simulations are ready. What we have done, we set clock as a clock signal with 100 nanosecond time period, and something interesting is observed. The counting is happening in the downward direction. We are going from 15 to 0 and then again going 15 to 0. What is the reason? The reason is our code. In our code we said that the triggering will happen at positive edge, and if you see here, at the positive edge of the clocks we are triggering these. If we would have done at the negative edge, then we will get the up counting. So let us quickly change the code and see that what we are saying, is it going to work or not. So here we will simply replace all the positive edge with negative edge, okay, and after that what we need to do is we are going to save it and run the simulation again. It will ask that close the already opened simulation. We said yes, and now we are going to generate the simulations again. I had done this intentionally because we should know very clearly that what can be the significant change or the effect of choosing positive or negative triggering in the counter design. So I go to clock and say force clock. I set it 0 to 1, 100 nanosecond, and now I run my simulations. And now you can see when I zoom it, now the counting is 0, 1, 2, 3, 4 till F. This is hexadecimal. You can right click and say radix is unsigned decimal. Zoom it, and now you can see that 0, 1, 2, 15 and then again 0. So this is very important, that how do we trigger our counters, the different bits. If you trigger at negative edge, you get up counter. If you trigger at positive edge, you get down counter. So student, now we know about one directional counter. Let us design a bidirectional counter. That means one single counter which can count in any direction at any moment. We'll talk about that in our next video. Keep learning. Thank you.